Alright, so today we're going to focus on natural log integration, along with integration with E, integration with exponents in general. Okay, so the natural log rule for integration you have the integral of dx over x equals the natural log of the absolute value of x plus c, or the integral of du over u equals the natural log of the absolute value of u plus c. All right, so let's say, for example, if you wanted to integrate 2 over x dx. Okay. The one thing about this one is you're going to actually move the dx to the numerator, and it works just fine. Okay, so you have the integral of 2 over x dx. You can actually just rewrite that, bring that 2 out to the front. Run out of lead. Really just 2 times the integral of d over x, well, dx over x, which will give you 2 times the natural log of absolute value of x. Too hard. Really. Plus c. Well, and really you don't have to put the 2 times c, because 2 times a constant will still give you another constant, so you just have to really multiply the c here. Okay. And then remember, with natural logs, you have the power rule. Move that up a little bit. Okay, so you have the p times natural log of x equals natural log of x to the power of p. Just those old rules that you probably forgot about. Okay, so this one can actually become natural log of absolute value of x squared plus c. And since x squared is always going to be positive, you don't really need the absolute value sign there. So you can just make it natural log of x squared plus c. All right. So any questions on that one?
On a test, would you rather have it as 2 natural log of x, or the natural log of x squared?
Either one of those would be okay with me.
Okay.
Yeah. I'm more worried about like the process than the final little tidbit. All right. Any other questions on this?
Do you want us to have the dx in the numerator?
You don't have to. It's just that it kind of makes it a little bit easier. You'll kind of see in other examples where it's dx over x or du over u. It's a little bit easier. But if you're more comfortable with it on the side, you don't have to. All right. so let's say, for example, we wanted to evaluate the integral from 0 to 3 of x over x squared plus 1 with respect to x. Okay. And this is where the u substitution comes in. Oh. Can everybody see this okay? This pencil seems like it's a little bit light. All right. Okay. So first, if we let u equal x squared plus 1, then the derivative of u with respect to x would be 2x with respect to x, or 2x dx. Okay. So that gives us our u and our du. Okay. So if you go to integral from 0 to 3 of x over x squared plus 1, and if you want, you can put the dx up there. You would have du over u, except your du is 2x dx. So you just divide both sides by 2, and you have du divided by 2 equals x dx. So now you can replace that x dx with du divided by 2. And you already have your u here. Okay, so this will actually become the integral from 0 to 3, and that x dx gets replaced with du over 2, or 1/2 du, it doesn't matter which one, over x squared plus 1, remember that's your u. Okay, so you can just get that 1/2 and bring it right to the front. So you have 1/2, integral from 0 to 3, your du over u. Okay, and now you can just go ahead and plug it in. Okay, so that's going to equal 1/2 the natural log of absolute value of u plus c. Okay. Oh, I almost got my, don't need the plus, bless you. Don't need the plus c because it's a definite integral. Okay, so that's from 0 to 3. Now that's x equals 0 to x equals 3. So if you wanted to, you can plug in, you can have your u, x of u, and all that other stuff. But what I do is, it's just easier to convert that u back to a function of x, and then so you can just plug back in the x value. So if you have 1/2, and instead of natural log of u, you make that natural log of x squared plus 1. Then your x equals 0 and x equals 3 doesn't have to change into anything. Look. All right, so we plug those in. We have 1/2 times natural log of 3 squared plus 1 minus the natural log of 0 squared plus 1. Okay, so you end up with 1/2 times the natural log of 10 minus the natural log of 1. Okay. Natural log of 1 is just 0, so that disappears because it equals 0. Okay, so you're left with the 1/2 of natural log of 10, which if you plug it into your calculator will just give you around about 1.15, give or take. Okay. And that would be your answer. Bless you.
Okay.
All right. So any questions on that one?
1/2 natural log of 10?
For most of them, they'll say either leave it as an exact value, then you can just leave it like that. But if they say round to like the nearest 3 decimal places or something, then you just plug it in.
And also, it moves back to parentheses are on, I think, step 3.
Mm-hmm.
Is that because the x squared makes it positive and +1 it'll always
Yep, exactly.
have?
Yep, so whenever there's no possible way for it to be negative, you can just drop the absolute values. Okay, any other questions? Okay, now if that would have been x squared minus 1, then we would have left it as absolute values, because there's values that will make it negative. So. All right. Put that there. So let's say, for example, we wanted to evaluate the integral of secant squared x over tangent x dx. Okay. So in this case, we want to let u equal tangent x. So we know the derivative of tangent x is secant squared x. That means our du will equal secant squared x dx. All right, so just bringing our dx right up top, the integral of secant squared x dx over tangent x just becomes the integral of du over u. Let's clear that up a little bit. Okay. Which we know is the natural log, the absolute value of u plus c. Okay. So we just plug our u value right back in. So it's the natural log absolute value of tangent x plus c. Because there are some negative values of tangent x, so we couldn't leave it as anything other than the absolute value. All right, so any questions on that one? Okay, so let's try another one here. Okay, so let's say, for example, you wanted to evaluate the integral of 2x over x plus 1 squared with respect to x. Okay. Now in this case, we're going to let u equal x plus 1. Which means the derivative of u is going to equal 1 dx, or just dx. Okay, so we know here. Oh, where do you go? Ah, there we go. Okay, so notice that the integral of 2x over x plus 1 squared, or 2x dx, doesn't work here. Okay. Mainly because you have no x dx here. And when you run across that, you can kind of tweak the problem a little bit. Okay. Nope. Does not work. Okay, so since u is equal to x plus 1, we can let, clean that up a little bit. X equal u minus 1. Okay, so now, move that up a little bit. We have the integral of 2x over x plus 1 squared dx can equal the integral of 2 times u minus 1. And remember, x plus 1 is our u. So that becomes u squared. And our dx is just du. Okay. So if we wanted, we can bring that 2 right out to the front. Oh, there, sorry about that. Okay, so we bring our 2 out to the front, and we're left with u minus 1 over u squared du. Okay, so we get that one, and we just separate it. So you have 2 times the integral of u over u squared minus 1 over u squared. Nope, du. Sorry about that. Okay, so this first one simplifies to 1 over u. Oops, actually should have left that 2 there. Instead of trying to squeeze, let me just write it with a little more room. Integral of u over u squared du minus 2. I keep forgetting my 2. There we go. 1 over u squared du. There we go. All right, so once you do that, you just simplify it and you can integrate like you normally would. So 2, this just becomes the integral of 1 over u or du over u minus 2, and you can integrate that as u to the negative 2 du. Okay, so since that's your du over u, if you decide to take it up to the numerator, you can do that. That actually equals, bring that up a little bit, 2 times the natural log of u minus 2, the integral of u to the negative 2, remember that's n plus 1 over n plus 1, so that would be u to the negative 1 over negative 1. Okay, so that actually will give us, make sure I got enough room, 2 times the natural log of u, which is x plus 1. Actually, that, well, still values that can make that negative. Minus 2 times u to the negative 1. So that would be x plus 1 in the denominator. Plus c.
Plus 2 over
Oh,
x.
yep, plus, yep. Thank you. Because it was already minus. All right. So any, yes.
Okay, so I got the same thing, but what was your process with the transferring from the last step?
Wait, this one?
Well, that one and the one before it, for the second term.
For, oh, you mean for this step?
Yeah.
Oh, that's just the integral of x to the n dx is just going to be x to the n plus 1 over n plus 1. So it's the same thing with u. If you differentiate with respect to u, I mean integrate with respect to u, So u to the n du is just going to be u to the n plus 1 over n plus 1. But in this case, negative 2 plus 1 over negative 2 plus 1 just gave us a negative denominator. So you had u to the negative 1
Yeah.
over negative 1.
I just don't know that I've ever seen that form, but it's the same process.
Oh, really?
Yeah,
Oh.
it's the same process that I've been using, but I've never seen the notation for it, for sure.
Oh. Well, sometimes my methods are a little different. So if something doesn't look familiar, just let me know. Yes.
Question.
Mhm.
You have to use both integration, finding the derivative and also manipulating the equation to get the final answer.
And some of them you will. It's very rare you'd have to actually do the u equals x minus 1, x plus 1, but x equals u minus 1. It's just one of those, if you run across one that doesn't work, you'll have to manipulate it. Most of the time it'll work.
In most cases where you work,
Mhm.
you most likely will just have to find the derivative.
Yep, you just have to find your u and your du, and you might have to multiply your du or divide it
Oh, by
in some
the
cases.
constant.
Exactly, just to make it fit.
Gotcha. All right.
All right, any other questions on this one? All right. All right. Okay, so let's say if we have, let's say if you wanted to evaluate the integral of 1 over 3x plus 2 with respect to x. Okay. And I'll give you a minute to start on this one.
So let's say 3x plus 2?
Yep, 3x plus 2. All right, so let's get started on this one. Okay, so the first thing you want to do, let u equal 3x plus 2. So the derivative of u, that disappears. Derivative of 3x is just 3 with respect to x. Okay. So if you divide both sides by 3, du divided by 3 equals dx. Or you can make it 1/3 du. Okay, so that means your integral of, if you bring your dx up to the top, you can do that. Dx over 3x plus 2 is just going to equal the integral, your dx, remember that's 1/3 du, and your 3x plus 2 is your u. Okay, so if we bring that 1/3 out to the front, we have our integral of du over u. Okay, and now we just plug it in. So you have 1/3 times natural log of u plus c. We replace our u with our 3x plus 2. So 1/3 natural log absolute value of 3x plus 2 plus c. Now, if you wanted to, using that same power rule for natural logs, you can bring that 1/3, put it up front. So you have the natural log of 3x plus 2 to the 1/3 power. And you can put that in absolute values if you want to, plus c. So either one of those would be okay. All right, so any questions on this one? All right. Okay, so let's say if we have, I should have enough room for the next example. I'll just put it on another sheet. Instead of trying to cram it on one sheet of paper. Okay, so let's say if we wanted to evaluate the integral from e squared to e to the 4th of natural log, wrong one, of x and that entire natural log is cubed all over x with respect to x. We'll bring that down a little bit. Okay. Now in this case, we're going to let u equals natural log of x. And derivative of natural log of x is 1 over x. So our du is going to equal 1 over x with respect to x. Okay. So if you look at this one, so e squared from e to the 4th of natural log of x to the 3rd over x with respect to x, you can actually rewrite it. E squared e to the 4th natural log of x to the 3rd times 1 over x dx. Okay, so in this case we have our u and we have our du.